morning. This is Dr. Muhammad Imdadul Haq. I will be dealing with the course Econometric Methods. At the very onset, we start with what's the definition and scope of econometrics. Econometrics is an empirical estimation of causal relationship between variables. The term econometrics is derived from two Greek words, oikonomia, meaning economics, and metron, meaning measurement. Altogether, it means economic measurement. Basically, econometrics is an amalgamation of economic theory, mathematical economics, economic statistics to provide numerical estimates for the parameters of economic relationships. These parameters may be elasticities, as in the case of demand equation, or propensity, as in the case of consumption function. So, we summarize the scope of econometrics using two definitions. The first one by Goldberger. He said econometrics is a social science in which the tools of economic theory, mathematics, and statistical inference are applied to the analysis of economic phenomena. Second, by Thiel, econometrics is concerned with the empirical determination of economic laws. So, in economics, our concern is to analyze and predict economic phenomenon. For that purpose, we construct a model. A model is a set of relationships between variables, and this relationship is expressed using the mathematical concept of function. Example, Q is equal to Fp, that is quantity demanded is a function of price. C is equal to Fy, that is consumption is a function of income. To understand econometrics as a separate discipline, we need to understand its difference and relationship with mathematics and statistics. Mathematical economists will suggest a specific functional form. Consider a concrete functional form QD is equal to alpha minus beta P. Quantity demanded is linearly related to price, and alpha and beta are the coefficient. Economic theory simply tells us the negative relationship between quantity demanded and price, but neither the economist nor the mathematical economist is concerned with the estimation of the parameters alpha and beta. And the concern of econometrician is estimation of parameters. It is important in many areas, especially for decision making, economic planning, government and businesses. Let us take an example. Say, we have the given data for price and quantity demanded. We can plot the data and present it as a scatter diagram. Now, in order to meaningfully interpret the scatter diagram, we draw a trend line. This trend line can be constructed using the econometric method of regression. Let's see the calculation for this demand function. So, in the first column we have price 1, 2, 3, 4, 5. For simplicity we have taken it like that. And in the second column we have quantity demanded. We take the mean first. We take the mean of price. We say denote it by x. So, x bar is equal to 3. Quantity demanded we denote it by y. So, y bar is equal to 10. So, next we compute x minus x bar. So, the values are minus 2, 1, 0, 1 and 2. Then y minus y bar, the values are 5, 0, 0, 0, minus 5. Then we multiply these two, x minus x bar with y minus y bar, and we get the values minus 10, 0, 0, 0 and again minus 10. Next, we do the square of x minus x bar. So we get as 4, then 1, then 0, then 1 and 4. Now, we come to the formula for beta. The formula for beta, we will do the derivation at a later point, but at the moment the formula for beta is equal to summation x minus x bar y minus y bar divided by summation x minus x bar square. So we take the sum of the column x minus x bar multiplied by y minus y bar, that is minus 20, and then we take the next column x minus x bar whole square, it is 10. So minus 20 divided by 10, this happens to be minus 2. Next, we calculate the value of alpha. The formula is y bar minus beta x bar. So, y bar is 10. Then beta we have just now calculated minus 2 multiplied by 3. That is equal to 16. So finally, the last line, the last column, we are calculating y hat. Y hat is equal to alpha plus beta x. So in the first case, alpha is 16 plus minus 2 multiplied by x is 1. So this happens to be 14. Similarly, we take x is equal to 2, x is equal to 3, x is equal to 4 and x is equal to 5. So we get 14, 12, 10, 8 and 6. The trend line is nothing but the data points given in the last column of y hat. So we have the data and estimate the demand equation as QD is equal to 16 minus 2P. Here 16 is the intercept, that is when price is equal to 0, quantity demanded is 16 and the slope of the line is minus 2, that is with a 1 unit increase in price, the quantity demanded will decrease by 2 units. So econometrics provide answers to the question of how much change in one variable affects the other. That is, it provides answer to magnitudes of the relationship between variables. Econometrics provides empirical content to the economic theory. Now, economic theory makes statements or hypotheses which are qualitative in nature. For example, from microeconomic theory, we know that price and quantity are inversely related. But economic theory tells us nothing about the numerical measure of this relationship. It is an econometrician who provides a numerical measure of the relationship between variables. That is, econometrics provide empirical content to economic theory. Mathematical economist is also not concerned with the empirical measurement of the relationship. The concern of mathematical economist is to express economic theory in mathematical language. The relationship may be price and quantity suggested by economic theory may be expressed by a mathematical economist as QD is equal to alpha minus beta P. Econometrics presupposes economic theory expressed in mathematical terms using the language of mathematics and provides numerical estimates for this alpha and beta. An important thing to understand is that mathematics assumes exact relationship between variables, while econometrics assumes that the relationship between variables is inexact. The first diagram is an example of exact relationship. This is presumed by the discipline of mathematical economics. All the data points are on the line. The second figure represents an inexact relationship. Suppose we have data on the quantity and price plane and plot the data. All the data will not lie on the straight line. Some observations will lie above and some will lie below the straight line. It means quantity demanded is not fully explained by price. Quantity demanded is explained by many factors like the price of substitutes, price of complements, taste and preferences, etc. So, we can say that economic theory is qualitative in nature, but it tells nothing about the numerical measure of the relationship. Mathematical economics only expresses economic theory using the language of mathematics, but economic theory and mathematical economics assumes that the relationship between the two variables are exact. But econometrics presupposes economic theory expressed in mathematical terms like y is equal to alpha plus beta x and provides numerical estimates to this relationship, assuming that the relationship between variables is inexact. Next, we consider the role of economic statistics. Its role is to collect and organize data in the form of tables, graphs, and descriptive statistics. The statistician collects the data of price, quantity demanded, GDP, and other variables. His role is restricted to this only. He does not test economic theory. He may calculate mean, median, mode, standard deviation, but he is not concerned with further analysis. Meanwhile, a related discipline of mathematical statistics is concerned with analyzing experimental data. But in economics, we use observational data. The tools of mathematical statistics are more suitable for experimental data. Econometrics uses tools of mathematical statistics adapted specifically for dealing with observational data. It is the duty of the econometrician using data collected to estimate the parameters. Next, we move on to the methodology of econometrics. The first is statement of theory or the hypothesis. Here, we discuss the steps in econometric analysis. There are basically 8 steps. Let us take the fundamental psychological law, also known as the absolute income hypothesis, or commonly known as the consumption function, as given by Keynes. The first step in the econometric methodology is statement of theory or hypothesis. Econometric analysis presupposes existence of an economic theory specified in mathematical form. The first step is the statement of the theory. The fundamental law states that men are disposed as a rule or on an average to increase their consumption as their income increases, but not as much as the increase in their income. As income increases, consumption increases, but not by as much as the increase in income. So, this is popular. We have this delta C upon delta Y. This is more than 0 and less than 1. This is more popularly called as the marginal propensity to consume. As economic theory is qualitative in nature, it simply states the relationship between variables. It will not give the magnitude involved. The second step is the specification of the mathematical model of consumption function. Keynes did not give the specific functional form of the consumption function. He said that consumption and income are positively related, but the nature of relationship is not quantified by Keynes. A mathematical economist can specify the relationship between consumption and income, say y is equal to alpha plus beta x, where alpha and beta are the parameters, and the concern of an econometrician is the estimation of these parameters, alpha being the intercept coefficient and beta being the slope coefficient. If we specify this equation in the form of graph by taking consumption on say the y-axis and income on the x-axis, we will get a straight line. Y-intercept is alpha and slope is beta, and the straight line is the geometric representation of the equation y is equal to alpha plus beta x. This is an example of a mathematical specification of the consumption function. The third step is specification of an econometric model of consumption function. Mathematical model is not of considerable interest to an econometrician because mathematical model assumes exact relationship between variables. But in econometrics, it is assumed that the relationship between variables is inexact or stochastic, or you can say random. Hence, econometrics specify the model as y is equal to alpha plus beta x plus u, where u is the error term. U is the random variable with well-defined probabilistic properties. So the point is that if you collect data on consumption and income of say 200 families and we plot this on observation, they will not lie on a straight line. Some observations will lie above the line, some observations will lie below the line, and some observations may lie on the line also. That is, the distance between observation and the line, it may be positive or it may be negative. Thus, in an econometric model, the relationship between variables is assumed to be stochastic or inexact. Stochastic means there is no one-to-one correspondence between x and y. That is, in addition to x, there may be other factors affecting y. The fourth step is the collection of data. To estimate the model like this, y is equal to alpha plus beta x plus u, data on consumption and income is required. Our concern is estimation of parameters alpha and beta. Remember, you can collect your data, that is your own data, that is primary data. You can use data collected by someone else, secondary data. You can use data on an individual household. You can use aggregate data and all these types. The fifth step is estimation of the econometric model. Once we have the data, then we apply the tools of econometrics. It is nothing but say the regression analysis. Using regression, we estimate alpha and beta. Suppose we estimate a model y hat is equal to 20 plus 0.7x, where Y is consumption, X is income. It implies that when income is 0, consumption is 20, and there is 0.7 is the beta value, that is, as income increases by 1 unit, consumption on an average increases by 70 units. Sorry, 0.7 units. The sixth step is hypothesis testing. You know from your basic statistics that it is our primary concern is estimation of population parameters, say alpha and beta. But to estimate these parameters, the entire data must be available. But in most cases, we have only a sample. From the sample, we estimate what is known as sample statistics or estimator. Sample estimators are used to make inferences about the population parameters. The seventh step is once hypothesis testing is completed and the estimated model is reasonable representation of reality, we can use the estimated model for two more purposes. One is forecasting, and the next purpose forms the eighth step, that is the use of estimated model for policy analysis. Next, we go on to the type of data and variables. A broad classification classifies data into time series, cross-section, pool, and panel data. Time series data is the data collected on variable at different intervals of time. Depending on the interval of time series, this time series can be classified into, say, daily, example, stock prices; weekly, example, money supply; monthly, example, consumer price index; quarterly, example is GDP; yearly, example is GDP; and on decennial, that is, example is census. Then there is cross-section data. If the data on a variable is collected on a particular point in time, it is cross-section data. As an example, an independent researcher to estimate a consumption function collects data on consumption and income at a particular point in time. The third one is pool data. It means data on cross-section is collected year after year. Suppose we collect data on consumption income for 100 families in 2020, then again 100 families in the year 2021, then again the 100 families in 2022, then we combine or pool together all these data sets. The next classification is of panel data. It is a special type of pool data where the same cross-sectional unit is sampled year after year. If, say, for 100 families, the data is collected year after year in 2020, in 2021, in 2023, and again in 2024, then it is called panel data. Now, we discuss the categorization of variables. There are four categorizations of variables: ratio, interval, ordinal, and nominal. Let's discuss the characteristic of variables categorized as ratio data. They are called as quantitative variables. Now consider a variable x taking values x1 and x2. So variable x is considered to be ratio scale if the three conditions are satisfied. First, x1 is divided by x2 and this is meaningful. Second, distance of x2, distance that is x2 minus x1 is again meaningful. Third, there is a natural ordering like x2 is greater than x1. A ratio scale features an absolute 0 point. A common example of ratio scales are the macroeconomic variables like GDP and all. The next categorization is interval data. If only second and third condition is satisfied and not the first one, then the variable is of interval type. That is, the distance x2 minus x1 is meaningful and there is a natural ordering like x2 is greater than x1. Consider different years. Distance between 2 years is meaningful, but you cannot divide 1 year by the other. There is ordering also. So an interval scale is characterized by numerically equal distances on the scale representing equal values in the measured characteristics. The interval scale ensures that the difference between any two consecutive scale values remain constant. Say the gap between the values 1 and 2 is same as 2 and 3, and likewise between 5 and 6. In other words, there is a consistent or equal interval between scale values, and the distances between descriptives are known. A common real life example is temperature scale. Attitudinal data, again obtained from Likert scale, is also an example of interval data. The third categorization is of ordinal data, which has only the third property. That is, there is a natural ordering like x2, and it is, say, x2 is greater than x1. So ordinal data is used in indifference curve analysis, and ordinal data is a ranking system where numbers are assigned to subjects to signify the relative extent to which the objects possess a certain characteristic. This type of scale enables the determination of whether an object has more or less of a characteristic compared to other object. But it doesn't provide information about the specific magnitude of the difference. In essence, an ordinal scale denotes the relative position of objects rather than quantifying the exact degree of variation between them. If data is not having any of these three properties, then we have what we call as the nominal data. Examples are gender, caste, color. Nominal scale is a symbolic labeling system in which the number function solely as tags or identifiers for the categorization and classification of objects. Example of it are, say, Aadhaar number, student enrollment number, and likewise. All these four type of variables are used in econometrics. Now we move on to some of the terminologies. That is, we use y as dependent variable. It is also called as regressant, explained, endogenous, outcome, control variable. Similarly, x, which is generally denoted to be the independent variable, it's also called as explanatory, regressor, exogenous, covariate, and control variable. Now we move on to the next topic, that what is the difference between regression, correlation, causation. The term regression was originally introduced by Francis Galton in 1886 to study why there is a stability in the distribution of the height of the population. Galton observed that while there was a tendency for tall parents to have tall children and for short parents to have short children, the average height of children born to parents of a certain height tended to move or regress towards the average height in the entire population. In other words, the height of the children born to exceptionally tall or short parents tends to gravitate towards the average height of the overall population. Galton's principle of universal regression was validated by his associate Carl Pearson, who gathered over 1,000 height records of family groups. Pearson discovered that the average height of the son from a group of tall fathers was less than their father's height, and the average height of sons from a group of short fathers was greater than the average height of the fathers. This resulted in both tall and short sons regressing towards the average height of all men. In Galton's word, this phenomenon was described as regression to mediocrity. But today, we use the word regression in a different sense. Today, the interpretation of regression analysis is different. Regression analysis is concerned with the study of the dependence of one variable on the dependent variable or one or more independent variable with the view of estimating the conditional mean values of the dependent variable on the basis of known values of, say, independent variables. In the context of regression analysis, we need to consider the difference between a statistical and deterministic relationship. Mathematical economists suggest deterministic relationship between variables. Deterministic means functional relationship between the variables. In this specification, x completely determines y. But in regression analysis, we are not concerned with deterministic relationship. We are interested in a statistical relationship. Statistical relationship means relationship between variables are stochastic, characterized by what is known as randomness. For example, consumption is a function of income, wealth, taste, and preference, and so many other factors. But we do not know the exact nature of relationship between consumption and factors influencing it. So the nature of relationship between consumption and factors determining is statistical in nature, characterized by randomness, or we can say it is stochastic in nature. In regression analysis, we are interested in stochastic analysis and not in deterministic analysis. Next, correlation. It is defined as the degree of linear association between variables. Consider two variables, x and y. Correlation means the degree of linear association between x and y. In correlation analysis, the status of this variables is the same or symmetric. Both x and y have the same status in the correlation analysis. We cannot say one is dependent and the other is independent. But in regression analysis, the status of the variables is asymmetric. Means in regression analysis, y is the dependent variable and x is the independent variable. So the relation is asymmetric as one is independent and the other is dependent. Whereas in correlation analysis, the variables have the same status. The second group of concepts to be differentiated is regression versus causation. Regression analysis is concerned with the dependence of one variable on one or more other variables, but it need not necessarily concern causation. Our idea of causation must come from theory, that is, from outside statistics. It is the duty of the theoretician to suggest a cause and effect relationship. Statistics by itself cannot give what is known as cause and effect relationship. Cause and effect relationship should come from theoretical considerations rather than statistical consideration. This idea of causation is based on just theoretical considerations. So basically in our course of econometrics, we will be looking at linear relationships, and by linear relationship we mean that these relationship wherein the variables are linear. If the parameter is linear, then we cannot use many of or most of the techniques which are used over here in econometrics. So what we need variables, we need either a linear relationship, clear cut, or we need cases in which the variable may be linear, fine. And in those cases, these non-linear variable, even if there is a non-linear variable, it can be converted into a linear variable. Like take the first case, the three examples that are given over here, that is y is equal to alpha plus under root beta x plus u. Here, this particular equation is non-linear in parameter. Variable is x, no problem, but the parameter is non-linear. Now this we cannot use over in econometrics. We take the second one, the middle one over here, y is equal to a plus beta x square plus u. X square, that is, it is a non-linear relationship, but it is non-linear in variable. So this we can convert it into linear and we can work with it. There is no problem. The third one, there is an under root sign over beta and there is an x square. So it is non-linear in both variables and parameter. So this we will not be working with in our discussions on econometrics.